Today, we're going to explore how computers represent and process text. When we type letters, numbers, or symbols, it may feel natural to us as humans, but computers don't actually understand characters the way we do. At their core, computers only deal with numbers, specifically binary ones and zeros. So the question is, how do we get from a human-readable character, like the letter A, to something a computer can store and work with? That's where encoding standards come in. We'll begin with ASCII, the American Standard Code for Information Interchange, which was one of the first widely used systems to map characters to numbers. Then we'll see how Unicode expands that system to cover every language and symbol you can think of. Finally, we'll connect this to Python with functions like ORD and CHR, which let us move between characters and their numeric codes. So the big picture idea for today is understanding that text at the computer's level is really numbers in disguise. Now let's talk about why encoding is important. First, remember that computers at their core only understand numbers, binary values of ones and zeros. They don't have any natural way to understand letters, words, or sentences. That means if we want a computer to work with text, like displaying a name, storing a message, or processing a document, we need a system that connects characters to specific numbers. This is what encoding does. Encoding provides a standard that defines exactly how each character is represented as a number. For example, the letter A isn't just a symbol to the computer. It's stored internally as the number 65. Without a consistent standard, one computer might think 65 means A, while another might think it means something completely different. Encoding ensures consistency so that text can be shared and understood across systems and devices. ASCII stands for American Standard Code for Information Interchange. It was one of the earliest and most widely adopted systems for encoding characters into numbers. ASCII is a 7-bit code, which means it can represent 128 unique characters. This set includes uppercase and lowercase English letters, digits, punctuation marks, and some control codes like new line and tab. Later, to extend its range, an 8-bit version was introduced. This is often called Extended ASCII, and it allows for 256 possible characters. Different systems use slightly different variations of Extended ASCII. For example, Windows systems often use the Windows 1.252 character set, which added symbols like accented letters for European languages. So the key point here is, ASCII started as a 7-bit system for English text, and later versions expanded to 8 bits to cover more characters and symbols. If you'd like to explore more, the link at the bottom of the slide, ASCIIcode.com, gives you a full chart of the ASCII table with all the characters and their numeric codes. ASCII worked well for English, but it was too limited for the rest of the world. What about accented letters, Asian characters, or even emojis? That's where Unicode comes in. Unicode is a universal standard that assigns a unique number, called a code point, to every character in every language, plus thousands of symbols and emojis. The idea is that no matter what language you speak or what device you use, the same character will always map to the same code point. This means Unicode makes text truly global. The quote on this slide highlights its purpose. Everyone in the world should be able to use their own language on phones and computers. The site shown here, unicode.org, is a great resource to explore code charts and see how many scripts and symbols are included. Now that we've seen ASCII and Unicode, let's look at 2 built-in Python functions that let us move between characters and their numeric codes, ORD and CHR. The function ORD takes a single character and returns its numeric Unicode code point. CHR does the reverse. It takes a numeric code point and returns the corresponding character. In this example, ORD pi gives us 960, which is the Unicode value for the Greek letter pi. CHR 960 gives us back the Greek letter pi. This shows the 2 functions are exact opposites of each other. One converts from character to number, the other from number back to character. These functions are extremely handy for working with text and programming. For example, if you ever want to shift letters, build a cipher, or generate a sequence of characters, you'll often use ORD and CHR. Here we see some examples of how Python lets us work with ASCII values using the two functions. ORD uppercase A returns 65, which is the ASCII code for uppercase A. ORD lowercase a returns 97, which is the ASCII code for lowercase a. ORD 0 returns 48, which is the ASCII value for the digit 0. And when we go the other direction, CHR66 gives us uppercase B. So these functions make it easy to move back and forth between characters in their numeric representations. Now here's the important connection. ASCII is actually a subset of Unicode. Unicode was designed to be backwards compatible with ASCII. That means the first 128 code points in Unicode are exactly the same as the ASCII table. So when Python shows us that the function ORD uppercase A returns 65, that's both the ASCII code and the Unicode code point for the letter A. This ensures that older ASCII-based text files can still be read correctly in modern systems that use Unicode. In other words, ASCII gave us the foundation, and Unicode expanded it to cover every language and symbol while keeping ASCII intact. Here we can see how Python handles characters beyond ASCII using Unicode. The line 1 prints 241. This is a character you'll find in Spanish and Portuguese, which isn't part of basic ASCII but has its own Unicode code point. The line 2 prints 20,013. This is a Chinese character that simply couldn't be represented in ASCII, but Unicode handles it without a problem. The line 3 prints 128,522, showing that even emojis are just numbers under the hood. And just like with ASCII, we can go the other way. CHR 128578 produces the slightly smiling face emoji. This slide makes it clear that Python doesn't treat ASCII and Unicode differently. ASCII characters are just part of the larger Unicode table, whether it's English letters, accented characters, Chinese, or emojis. They all map to numeric code points and can be converted back and forth using ORD and CHR. This is what makes Unicode such a powerful standard. It allows us to represent text from any language and even symbols like emojis on the same platform. Now let's put this into practice. I want you to write a Python program that prints all the letters from A through Z. Here are the requirements. You must use a for loop with the range function. You must use the CHR function to convert from numbers into characters. Think about what numeric values you need to start and end with in order to cover all uppercase letters. Remember that uppercase letters in ASCII start at 65, which is A, and go through 90, which is Z. Here's one possible solution. We use a for loop with range 65 and 91. Why 91? Because range stops one before the end, so this loop covers 65 through 90. Inside the loop, we call CHRI to turn each number into its character. We also add end equals single white space in the print function to print everything on the same line, separated by spaces. When we run this, we see the full alphabet from A to Z printed in order. This example shows how we can combine range, for loops, and CHR to generate sequences of characters. It's a simple but powerful way to connect programming logic with text processing. Let's wrap up what we've learned today. Computers don't actually understand text. They only understand numbers. Encoding provides a standard way to map characters to numbers so that text can be stored and shared consistently. ASCII was the first widely used system with 128 characters, and it became the foundation for text processing. Unicode expanded on this idea, giving every character, symbol, and emoji in the world its own unique number. In Python, the functions ORD and CHR let us move back and forth between characters and their numeric codes. So the big takeaway is, whether it's the letter A, a Chinese character, or an emoji, it all comes down to numbers underneath. ASCII gave us the starting point, and Unicode makes text truly universal. As you continue coding, remember, text isn't magical. It's numbers in disguise, and you now know how to work with those numbers directly. Thank you. This presentation was prepared by June Lee with the assistance of AI technology.